PU2 champions, so your first pre-board exams are very close. And haloalkanes and haloarenes is one of the most important chapter, not only because it can give you 9 marks in your exam, but also it is a very simple and easy chapter, and the questions here are very predictable. You have to just remember certain name reactions, some very important and easy mechanisms, and you can get 9 out of 9 from this particular chapter. So to help you with this, in this particular video, we are going to solve a lot of questions, all the important questions from this particular chapter, which are sourced from the question bank of this particular year that is released by the PU2 board. I have literally solved all the questions in 2 marker, 3 marker and 5 marker sections. Also, we have collected questions from the previous year questions so that you can know how repetitive these questions are. Okay, so in this video, we'll be solving questions. So before that, let's understand the blueprint of this particular chapter. That is how you will be getting questions in which sections. So this chapter carries, as I said, 9 marks. Okay, but how is this 9 marks distributed? You will be having 2 questions in the 1 marker section. Okay, it can be 2 MCQs or 1 MCQ and 1 FIB. That is the more probable combination based on the past year questions. But yes, you'll get 2 1 marker question. Then you will get 2 marker question, okay, in the section B. Section B, which carries 2 marks, there will be 5 questions. In that, 1 question will be from haloalkanes and haloarenes. In 3 marker section, this chapter has no role, and in the 5 marker section, you will get 1 question in the 5 marker section. And let me tell you, this 5 marker 1 question is a short question. You can very easily predict it, and if you watch this video and solve all the questions, then I can guarantee you that 9 out of 9 is definitely in your pockets. Okay, so let's get started. But yes, before moving to that, I just want to tell you, I have made a video, a very smart strategy. I have analyzed the blueprint very thoroughly, and I have give you 6 magical chapters. Okay, and if you complete this 6 magical chapters, you can easily score 60 plus out of 70. You don't have to go all the 10 chapters to get 60 plus. Okay, it is very easy with only 6 chapters, and in that also I have the one of the chapters haloalkanes and haloarenes. So definitely watch this video if you just don't want to prepare, but you want to prepare smartly and you want to get more with less time. Okay, please watch this video. And to revise the concepts of haloalkanes and haloarenes, I have also made a detailed one-shot video. Do watch that and understand all the concepts, then come for this video where we will be solving the questions. Okay, so children, let's get started now with the first part, that is previous year questions. Okay, so 2024 and 2025 questions are already included in the question bank, so I have collected questions from 2023. Okay, and after we are done with the PYQs, we will be moving to the questions of question bank released this particular year. So now let's see the first question. This is from 2023 March. Okay, so this was your MCQ question. Identify the chiral molecule in the following compounds. Now, what is a chiral molecule? See, if a carbon, we all know that carbon forms 4 bonds. Okay, so if all the 4 groups attached to the carbon are different, then we call it as a chiral molecule. Now let's see all the structures. If I have 2-bromobutane, okay, so if you have a structure like this, 2-bromobutane. Now, can I see that this particular carbon is chiral? Yes, definitely, because one side it has bromine, one side it has hydrogen, one side it has CH3, and the other side it has ethyl group, right? So since all the 4 groups are different, so yes, this is a chiral compound. We don't have to check for the other option. A is the correct answer. Next, when chlorobenzene is treated with sodium in dry ether, dash is formed. This is from the fill in the blanks. So if I have chlorobenzene, okay, and you treat it with sodium and dry ether. So first of all, you might have recognized the name of this reaction. This is Fittig reaction. Okay, and we get the product here, diphenyl. Okay, you get a product like this, and this is called as nothing but diphenyl. Okay, next. So okay children, let me just tell you one important thing, that I have done almost all the questions from the question bank in PYQs, but certain questions I have marked as VVI, means very important. So what you have to do is, when you go through this lecture, just write down these VY or just keep a mark of these questions, these very, very important questions. You should not skip these questions at any cost. Okay, if you are not able to do all the questions, don't worry, but make sure that you solve all the questions that I have either circled or I have noted as VVI. Okay, you have to do those questions before going to the exam. Okay, next, let's see the question. This question, explain the SN1 mechanism of conversion of tert butyl bromide to tert butyl alcohol. So this is the direct question. SN1 mechanism is asked. And what is in question number B? Give any two reasons why the aryl halides are less reactive towards nucleophilic substitution reaction. Now see, this particular question actually has three reasons in the book. Okay, so this particular question can be asked for two reasons also, three reasons also. So first let us discuss this one, then we'll go for option question number A. So why this, there is only less reactivity of nucleophilic substitutions on the benzene ring or in the haloarenes? So let us understand that first one. Now see, when you have this Rx or ARX, okay, now nucleophile is there. So the point is the nucleophile cannot directly attach here and remove the X. The first reason here is resonance effect. Because of this resonance, we have a partial double bond character here, right? So that is why it is very difficult to break this bond. That's the first point. Second point is due to the sp2 hybridization of this carbon. Now see, because this carbon is sp2 hybridized, this bond is very strong and it is very difficult to break this bond by a nucleophile. And the third one is, suppose in case the X leaves here. So what you will get? You will get something like this. Okay, this is formed, and this is a phenyl carbocation which is highly unstable because the positive charge is on the electronegative carbon, which is sp2 hybridized. So because of these three reasons, the nucleophilic substitution reactions on the haloarenes is not easy. Okay, now let's go to the first question, that is your SN1 mechanism. So here you have to mention both the steps and you have to write the mechanism. So the first step is what? Step number 1 is actually the formation of carbocation, right? Formation of carbocation. So here what happens in this particular structure, and also remember in step 1 there is a double-ended arrow, means there is a equilibrium symbol, and this is a slow step. Okay, so what will happen? First the bromine leaves here and we get a carbocation is formed and Br minus is there. And in the step 2, what is there? In the step 2 there is attack of nucleophile, right? So in step 2, what will happen? This OH minus can actually attack on this particular carbocation and you will get a product like this. Clear? Now we will move to next question, that is question number 4. So this is now PYQs from May 2023. That is maybe the second exam that is conducted or the supplementary exam. Which of the following has the highest melting point? Okay. Now if you remember that para-dichlorobenzene has the highest melting point. Why? Because it fits. It is, first of all, it is symmetrical in nature. Okay. Now when it is symmetrical, what will happen? It will fit better in the lattice. Okay. We can pack it very closely. Now let's understand. See, if you have para-dichlorobenzene, okay, the structure is like this. You have a chlorine here, you have a chlorine here, and another chlorine, another para-dichlorobenzene can be present here, and we can pack them very close to each other. But when you have meta-dichlorobenzene or ortho-dichlorobenzene, the bonds are present like this, right? For meta, it is we have like this structure, okay, and another meta we have structure like this. Okay, now it is very difficult to pack them because of the structure which is not symmetry. So that is the option number B here. Next, alkyl magnesium halides are known as, these are known as Grignard reagents, right? What's the structure? R MgX. Okay, next question, again here I have marked, the first question is write the equation for the two steps involved in the tert butyl bromide to tert butyl alcohol. We have already discussed this question, so you can understand how important is this SN1 mechanism question. It is asked again and again. Okay, next, explain Woods fatigue reaction and what are freons. So what is Woods fatigue reaction? So let me just give you an idea. We have three reactions here that you have to remember. First is Woods reaction, next is we have fatigue reaction, and the third one is we have Woods fatigue reaction. Okay, now see, in Woods reaction what happens? Rx reacts in presence of sodium and dry ether to give you RR. Okay, in Fittig reaction, what happens? ARX reacts in presence of sodium diether to give you AR or diphenyl. In Woods-Fittig reaction, you have RX plus ARX to give you a compound like this, AR and R. Okay, so these are the three types of reaction. If you remember in this way, you will remember it easily. So the question has asked about this one, that is Woods-Fittig reaction. So let me show you how you need to write the answer. Now see, for every time whenever there is any name reaction question, you have to follow this method. First you have to write the statement, and then you have to write the example. Whether it is asked or not, you need to always write the example. Statement carries 1 mark and your example carries 1 mark. Okay, so let's see. Question number, okay, B I will discuss. First, let's complete the C1 because on the space I have adjusted. Okay, what are freons? So the chlorofluorocarbon compounds of methane and ethane are collectively called as freons. Okay, so if you have CCl2F2, chlorofluorocarbons of methane or ethane are called as freons. Now let's do the B part, that is Woods-Fittig reaction. So when you take one alkyl halide and aryl halide, they give you alkyl arene in presence of sodium and dry ether. Okay, you can write the reaction, an example. Here you can take anything for X, you can mention anything for R, so it will be more clear. Okay. Next, we'll talk about racemic mixture. This is also a very, very important question. You need to know the definition. Now see, first of all, let's understand the concept of racemic mixture. So this is generally obtained in a SN1 mechanism reaction. Okay. Now we have already discussed the mechanism of SN1. So what happens? Suppose when in step 1, what happens? We get a carbocation, right? Carbocation is a planar molecule. Now in step 2 of SN1, what happens? The nucleophile can attack. Okay. Now the nucleophile can attack from both the sides. Now if the reactant is a chiral molecule, okay, if the reactant was a chiral molecule, then what will happen? It can be either D, means dextrorotatory, or it can be either L, that is levorotatory. Now what happens? Suppose the nucleophile was present, sorry, the leaving group, okay, suppose the leaving group was present on the top side, okay, and now after the carbocation has formed, the nucleophile is also attacking on the top side. So you will get one compound like this, where the nucleophile is placed on the same place where there was leaving group. That is your retention product. Okay, now let me just assume that the reactant was D or dextrorotatory. So here will also be dextrorotatory. Now also the nucleophile can attack from the bottom side. So you can have a possibility like this as well, right? And this one will have levorotatory, or it is denoted as minus sign. So what will happen in the sample? You will have equal mixture of both the enantiomers, and this racemic mixture will be optically inactive. Okay, so that is called as racemic mixture or racemic modification. Okay, so I'll show you how to write the answer. And yes, so just a minute. 1 second. Okay, so now let's see the answer here. A mixture containing, please see the definition properly, a mixture containing two enantiomers in equal proportions will have zero optical rotation, as the rotation of one is cancelled by the other. Is such a mixture is known as racemic mixture or racemic modification. Now here another question can also be asked, that is why the racemic mixture has zero optical rotation. Okay, so this can also be a question, and I think you have already understood the answer, that the rotation of one or isomer is cancelled by the rotation of another isomer because both are opposite and equal in proportion. Okay, so this also can be a potential question. Now let's move to the next question, that is your write the SN2 mechanism for the conversion of chloromethane to methanol. Okay, this is also important question. SN1, SN2 both are important. So here you can see first you have taken chloromethane and then OH is there, it will attack from the back side. So here what is this? This is a transition state formed. Okay, so a transition state is formed, and after that you can see that the OH is always attacked from the back side. Okay. Next, let's see the question from 2022 March. So we have explained Swartz reaction with an example. This is a name reaction. Then we have water Grignard reagent. This is also, these two questions 3A and 3B are very, very important. I have marked them. Okay. Next, name the poisonous gas evolved when the chloroform is oxidized in the presence of air. Okay. And light. Sorry. So what is Schwartz reaction? Schwartz reaction is the production of fluoroalkanes. Okay. So if you take the synthesis of alkyl fluorides. Okay. One second. The synthesis of alkyl fluorides by heating an alkyl chloride or bromide in the presence of metallic fluorides such as AgF, HgF2, COF2 or SbF3 is called as Schwartz reaction. Okay. Now see, as I told you, always you have to write down the reaction even if it is not asked. So this gives you 1 mark if you write the definition, and when you write the example, CH3Br with AgF will give you CH3F. This example will give you 1 mark, and total you get 2 marks here. Next question, what are Grignard reagent and write its general formula. Okay, so Grignard reagent are what? Alkyl magnesium halides. Okay, so when you take any when you take Rx and you treat it with magnesium and dry ether, okay, we get something called as RMgX. This particular compound is called as Grignard reagent. How do we define it? Alkyl magnesium halides are alkyl magnesium X halides having direct carbon metal bond. So here there is direct carbon metal bond, are called as Grignard reagent, and how it is represented? RMgX. Next question, name the poisonous gas evolved when chloroform, okay, is oxidized by air in the presence of light. So when chloroform is oxidized, we get a poisonous gas called phosgene, okay, called phosgene, and its formula is COCl2, and the structure is like this. Okay. Next question is from July 2022. What is a stereo center? Okay, so stereo center is similar to an asymmetric center, or that particular carbon which is having 4 different groups. Okay, that molecule is called a chiral, but that particular carbon which contains the 4 different groups is called as a stereo center. Okay, all the substituents attached to that carbon are different, and the mirror image of the molecule is not superimposed on the molecule, and such a carbon is called asymmetric carbon or stereo center. Okay, next, what is Finkelstein reaction, and write the equation. Again, this is name reaction, very important, and you have to follow the same mechanism, first definition and the reaction example. So Finkelstein reaction is for the preparation of alkyl iodides, right? Alkyl iodides are often prepared by reaction of alkyl chlorides or bromides with NaI in dry acetone. Now, what is this role of dry acetone? That is also a very good question. We will be solving it in the upcoming slides. Now, the reaction is known as Finkelstein reaction. Here you can see, when it is told that write equation, okay, always mention with X. If it is given write example, then try to write by giving, like using something in the form of Br, like you can use CH3Cl, CH3Br, anything. Okay, so Rx with NaI, and here I have to use dry acetone to get Ri plus NaX. Clear? Okay, next the question, write the equations for the step involved in the hydrolysis of 2-bromomethyl propane. Okay, it is very similar to what we have already done. So this question is solved. SN1 mechanism we have done with 2-methyl 2-bromopropane, and this is only this is also same 2-bromo 2-methyl propane. So you see how many times now, till now 3 times this question has been asked in just 2 years. So you can see how important is this question. Next, explain the Friedel-Crafts alkylation reaction with taking chlorobenzene as an example. Friedel-Crafts alkylation, again a name reaction. So first definition and then you have to write the reaction. So chlorobenzene reacts with alkyl chloride in presence of anhydrous aluminium chloride to form ortho-methyl chlorobenzene and para-methyl chlorobenzene. Okay, so you can see you have chlorobenzene, you have CH3Cl and AlCl3, and here CH3 will be added at ortho position and CH3 will be added at the para position. Okay, so you get 1 chloro 2-methyl benzene, and then you have 1 chloro 4-methyl benzene. Okay, these both are important compounds. Okay. Okay, so students, now we have done 2022, 2023 questions. Okay, 24, 25 questions are there in the question bank, so I have not taken them separately. And now we will be solving the questions from the question bank that is released by the PU boards. Okay, it is released by the PU boards for the year 2025 and 2026. Okay, the latest question bank I have taken, and I have solved all the questions from them in 2 marker, 3 marker and 5-marker section. Now here might be a doubt that, ma'am, from this chapter we will not be getting 3-marker questions, so do we need to solve them? Yes, you need to solve them. The reason being, in 5-marker section it will be either, sorry, just a minute. See, in the 5-marker section, it will be either 2 plus 3 or 2 plus 2 plus 1. Okay, so you will not be getting one question of 5 marks. Okay, there will be parts, and there this 3-marker, if you have practice, you can easily solve the 5-marker questions. So now let's start with the first question, that is your 2-marker section. Okay, so I have not considered here MCQs question. For that we can have a separate video. This is for all the theoretical questions. Okay, so the first question here is classify, one second, let me just, yeah, classify the following into geminal and vicinal dihalides. Now what is geminal and what is vicinal dihalides? So when you have on the same carbon 2 chlorines or 2 X groups are present on the same carbon, we call it geminal. And what is vicinal? When you have adjacent carbons and they are having X groups, that is called vicinal, right? So now if you have ethylene dichloride, okay, now see, from the name, whenever you have dichloride, it is for the vicinal dihalides. Okay, it is for the vicinal dihalides. And methylene chloride, okay, now when you have on the this particular type of name, there is no di used in the chloride part, this is the geminal dihalide. Please remember, if di is attached with chloride, then we'll call it a vicinal one. Okay, and next question, classify into allyl and vinyl halides. This is very simple. Allyl means what? You have this carbon that is having X, means the carbon which is attached to sp2 carbon. Okay, so one second, the carbon which is attached to sp2 carbon, that carbon contains X. See, the carbon which contains X, that is sp3 hybridized, but it is connected to a sp2 carbon, that is called as allyl. Okay, that is the definition of allyl. And what is vinyl? Vinyl is when you have one carbon and that carbon is directly attached to X group. Okay, the sp2 carbon is directly attached to X group, that is called as vinyl. Okay, so now let's see, we have 3-chloropropene. So let's draw the structure. If I have 3-chloropropene, right, now here you see this carbon is sp3 hybridized, it is attached to the sp2 carbon, so obviously this one is your allyl structure. Now 1-chloroethene, so when you have like this, so here chlorine is directly attached to the sp2 carbon, so this is vinyl. Okay, next, give one example for each of the following: geminal dichloride and vicinal dihalide. So you can write down any example. So for example, here I can write for 3A geminal, I can write CH2Cl2, and for B I can write down CH2, CH2, Cl and Cl, right? Okay, next let's do some questions. So all these questions which I have marked with what I'll say circled, okay, these all are important questions and can be asked, so you need to prepare those questions. Why the free radical halogenation alkanes method is not advised for the preparation of haloalkanes? Why we do not use this free radical mechanism for the preparation of haloalkanes? That's the first question. Now what is the answer for this one? Okay, the first one is, when you do free radical mechanism, the product is not selective. Okay, you get a mixture of mono, di and polyhalogenated products. You get a mixture and you need to separate them. So there's a lot of back end work is there. We don't get the desired product directly. So that is why this is not a preferred method. Second, fifth question, haloarenes cannot be prepared from phenols. Okay, now if you see that uh, if I compare, I'll just go back here once again. See, let's just discuss something about question number 5. Now, haloarenes. Okay, see, in case of, for example, if I have CH3OH and if I treat it with SOCl2, I can easily get CH3Cl. But the same thing does not exist for if I have phenol OH, and if I treat this one with SOCl2, okay, I won't be getting here, OH is not getting replaced with Cl. So the question is being asked like that, that haloarenes means chlorobenzene, okay, cannot be prepared from phenols. Why? So the reason is again very simple. When you have this one, right, here this OH bond can break easily and can leave the compound. But here what happens? We have resonance, we have a partial double bond character. So this bond is very strong, the COH bond, okay, in haloarenes. The COH bond in haloarenes is very strong. Now, why it is strong? It is very strong due to resonance, right? But if you simply compare the normal, so here I'm just putting this as like this. Once again, okay, just imagine this is a part of the ring. But if you have a normal CH3OH bond, here this bond is not, there's no resonance, nothing. This bond is weak, right? So that is why in case of phenols, you cannot directly replace the OH with chlorine. But in case of in case of alcohols, we can directly replace the OH group with the halogen group. Okay, so that is why haloarenes cannot be prepared from phenols. I'll show you how to write the answer. Don't worry. So I hope you have understood. Now let me get back. Yeah. So what is happening? The AROH, okay, bond is stronger due to the partial double bond character. So nucleophilic substitution does not occur, preventing the formation of haloarenes. Next question is Schwartz reaction and Finkelstein reaction. Name reaction anyway is very, very important. And I think both the reactions we have already discussed, right? So that is why I'm not going again. You can just note down that these two questions will be asked definitely in the 2-marker section. Next, we'll go to question number 8 here. Write the product obtained when toluene reacts with Cl2 in sunlight and Cl2 in FeCl3. Now, let me tell you, this question is very, very tricky question. Okay, if you are not thorough with the concept, you will get this question wrong. So see, if you have, what is this one? Toluene, right? Toluene. See, when you treat it with chlorine in sunlight, okay, so that actually follows free radical mechanism, okay, and what happens? The chain is halogenated, okay. Now what is this one? The chain one, okay, the carbon which is present in the outside the ring, that gets halogenated. So you will get a compound here like this, CH3Cl, okay. Now if you use chlorine with FeCl3, okay, so that is a chlorine will be attached to the ring here, okay, and you will have CH3 group and you will have ortho and para product, but yes, para is the major product, okay. So this you will get in the chain and this chlorine will be attached to the ring, okay. This is very important question. Next, why iodobenzene and fluorobenzene cannot be prepared from halogenation of benzene? So if you have seen the methods of preparation of haloarenes, mainly we were focusing on the preparation of chlorobenzene and bromobenzene, but we were not able to prepare fluorobenzenes and iodobenzenes using haloarenes. So what is the reaction? What is the reason for that? Okay. Now the first is why we cannot have iodobenzene. The reason is with iodine, no, when you react, the reactions with iodine are reversible, okay, and in nature, and that is why we require the presence of an oxidizing agent like HNO3 or HiO4 to oxidize the Hi formed during the iodination, okay. Now what is the product of the reaction? See, let's first talk this one. So if you are for example, if you are reacting, okay, with, for example, if I have Cl2 and FeCl3, okay, so what it will do, it will replace one of the hydrogen with chlorine, okay, and the byproduct formed is HCl, this H and one another chlorine will get you HCl. Now when, if the same reaction happens with iodine, here you will get Hi, right? So what will happen here is the Hi actually can react with this one again and can give you iodobenzene. So that is why you need to have some oxidizing agent like HNO3 or HiO4 which can oxidize this Hi to iodine, means you can convert this Hi to I2. Okay, so that is the point. So that is why we do not have iodine reactions easily. And fluoro compounds are not prepared because of their high reactivity of fluorine. They are highly reactive and we cannot prepare them by this method. Okay. Next, question number 10, write the structures of different dihalogen derivatives of propane. This is very simple question. See, I have not marked here any of the question. These are not very important questions. Okay. But yes, since it is there in your question bank, you need to solve. Dihalogen derivative means you have to write different products. One is I can have 2 carbon, 2 chlorine. The second possibility is on the first carbon, we are having two chlorines. The third possibility is on the second carbon, we are having two chlorines, right? So you will have three different, I can say, isomers are possible. So this is actually question number 10. Sorry. Next. Write the reactions involved in the preparation of bromobenzene from aniline. Okay. So bromobenzene from aniline, if I go, how we can prepare? See. Second. Yes. So if I want to prepare bromobenzene from aniline, so first you have to take aniline. Okay, this is your Sandmeyer reaction. Then you have to treat it with nitrous acid. So that will give you benzene disonium chloride, right? And once you have formed benzene disonium chloride, what you can react here? You can react this one with Cu2Br2. Okay, that is the salt of copper and bromine. That will give you bromobenzene. Okay, that is question number 11. Next, Sandmeyer reaction. This is the same reaction. You have to write the definition and then the reaction. Okay, so yes, the Sandmeyer reaction is a type of substitution reaction that is widely used for the production of aryl halides from aryl disonium salts. Copper salts like chloride, bromide or iodide are used as catalyst in this reaction. So this is the definition and this is the reaction. So first aniline, right? Aniline with nitrous acid is converted to benzene disonium chloride. Then with Cu2X2 you can get chloro or bromobenzene. Now from here, if you treat it with Ki, okay, you can also get iodobenzene. Okay. Next, we'll talk another question, that is question number 13. Haloalkanes are very slightly soluble in water. Okay, even though they are polar, but they are very slightly soluble in water. What is the reason? Now see, let's understand the reason first. You have Rx molecules, okay, and you have water molecules, right? Now there is force of interaction between Rx, right, and there is force of interaction between the water molecule. Now when this Rx will get dissolved in water, what will happen? You have to break. See what will break? Rx, Rx. This interaction has to break. Water interaction has to break. And what will form? You have to form Rx and water interaction has to form, right? And whenever there is breaking, it is endothermic, and whenever bonds are forming, that is exothermic. So here energy will be required, or you have to give energy, and here the energy will be released. Okay, so the thing is, the energy released should be more than the energy that is required to break the bonds. Okay, means whatever the energy that is released here when Rx and water bonds are forming, whatever energy has to be released, that energy should be more than the energy required to break the interactions between Rx and water, but that does not happen in this case. So that is why the solubility is very less. So let's see how you can write down. See, the haloalkanes are slightly soluble in water. In order to dissolve the haloalkane in water, energy is required to overcome the attraction between the haloalkane molecules and break the hydrogen bonds between the water molecules. We need first to break these bonds. Okay. Now the less energy is released when the new attractions are set up between the haloalkane and water molecules, as these are not strong as the original hydrogen bonds in water. So the interactions between the Rx and the water is not as strong as the water interactions due to the hydrogen bonding. So that is why the energy released here is less, which is not sufficient to break the interactions between Rx and water molecule. So that is why they are less soluble. Next, give two differences between SN2 and SN1. This is an important question. So how we can write down? You can write many differences. I have just given you some points. So this is unimolecular, this is bimolecular, this is first order, this is second order, two steps, one step. Here rate depends on the substrate only, depends on both substrates and your nucleophile. Carbocation is formed, no carbocation is formed. Here you can write transition state is formed. So that is the difference. Next, what are optically active compounds, and name the instrument used to measure the optical activity. So those compounds which can rotate the plane polarized light are called as optical active compounds. And what is the instrument name? That is your polarimeter. Okay, the compounds which can rotate the plane polarized light are called as optically active compounds. The device is polarimeter. Next, how the plane polarized light is produced, and name the instrument used to measure optical rotation. So what is plane, how the plane polarized light is produced? So plane polarized light is produced by passing ordinary light through nickel prism. Okay, and what is the device? Again, the device name is here polarizer. Sorry, polarimeter. Sorry, one second. This is polarimeter. Okay, 16 done, 17 done, 18 done. Next, water enantiomers. This is important questions. Okay, 19th one is important, 16 is important here. What are enantiomers, and name one physical property which differentiates the enantiomers. So enantiomers are non-superimposable mirror images of each other. Okay, so the stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. Now, in which property they differ? They differ in the direction of plane polarized light. So one enantiomer will rotate it in clockwise direction, other enantiomer will rotate it in anti-clockwise direction. Okay. Next, write the product formed when ethyl bromide reacts with KCN and AgNO2. So with KCN you will get ethyl cyanide, and with AgNO2 you will get nitroethane. Okay. Now similarly, remember with Ag, sorry, yeah, remember here with AgCN, okay, you will get isocyanide. Okay, and with KNO2 you will get RONO. Okay, next we'll talk about question number 21. This is important. What is ambidentate nucleophile, and give one example. So those nucleophiles which have two donation sites which can bind from two different sites, like CN. Okay, CN can bind from C also, N also, right? So that type of nucleophiles are called as ambidentate nucleophiles. So groups like cyanides and nitrides possess two nucleophilic centers and are called as ambidentate nucleophiles. Okay, already we have given here examples. Next, what is Grignard reagent and write its formula? Already we have solved this question in the previous slide, so I'm not discussing it again. Complete the reaction and the name of the reaction. Okay, C6H5Br and CH3Br is there. So you can see here, what is it? One is your alkyl bromide, another is aryl bromide. So what is this product you will get? Product here will be C6H5 and CH3. And what is the name of the reaction? This also we have discussed. This is Wurtz-Fittig reaction. Okay, done. Next, which of the following will react faster by SN2 mechanism? So what is the order of SN2? 1 degree, 2 degree, and then 3 degree, right? So, and here you can see both are 1 degree. So what we will see, which is a better leaving group. So iodine is a better leaving group, so that will react faster. And here this is tertiary and this is primary, so primary will react faster. Next, what is meant by racemic modification? Racemic mixtures are optically inactive. Give reason. Already I have discussed this question. A mixture containing two enantiomers in equal proportions is known as a racemic mixture. It has zero optical rotation. Why? Because one will rotate it in clockwise and another one will rotate it in anti-clockwise direction. Right? Already discussed. Let us see the next question. Complete the following reaction. Okay, C6H5MgBr and C2H5O minus Na. So here we will get the product C6H5O C2H5. Okay, ether will be the product, and here KNO2 is there, so it adds ONO group, right? So you have CH3ONO. Okay, remember, if you have AgNO2, directly NO2 will be attached. If you have KNO2, then ONO will be attached. Next, we'll see this question is important. Question number 28. One second. Although chlorine is electron withdrawing group, yet it is ortho-para directing in the electroaromatic substitution reaction. Why? Now see, chlorine has both minus I and plus R effect. Okay, because it is having lone pair, it can donate electrons and increases the electron density at ortho and para position. So that is why it is, you can write down, it is a ortho-para directing. Okay, so this is the answer you can write. 28th question. The lone pairs of electrons on chlorine participate in the resonance with the benzene ring, making the ortho and the para positions negative. Okay, as a result, it is ortho-para directing group. Next, what is Sadzev rule? This is important. We have already explained, discussed this in the lecture. So when you have dehydrohalogenation, okay, you're removing one halogen and one hydrogen, the preferred product is that alkane which has the greater number of alkyl groups attached to the doubly bonded carbon atoms. Now see, you have this doubly bonded carbon atoms. Now in these groups A, B, C, D, okay, in these groups, okay, if we have more number of carbons, then it is more stable. Now explain with an example. So if you see 2 bromopentane, okay, here you can see this is an alpha hydrogen and this hydrogen is also an, sorry, not alpha, beta hydrogen. So there's a possibility that I can remove this one, or there's a possibility that this HBr will be removed. So if this HBr will be removed, you will be getting alkene in the first and the second carbon. Now let's analyze this particular structure. You have CC and here you have H and here you have H, here you have H, and then here you have carbon. So around this double bond, if you see, we have 3 hydrogens and 1 carbon. Now if I have this HBr, if it is removed, we'll get a double bond on the second and third carbon right here. And if you see the structure here, it is like H, CH3, and here I have H, and here I have CC. Now if you see around this double bond, okay, you have 2 carbons and 2 hydrogens. Okay, now what does the rule says? That more the number of alkyl groups, better will be the stability. So here I have more number of alkyl groups, 2 carbons are present, so this is why more stable, and you can see 81% product is formed here. Now next question number 30, Wood's reaction. I have already explained, you can see how to write. So just a minute. Yeah, so Wood's reaction, you have to just take 2 Rx, okay, and if you treat them in presence of sodium and dry ether, okay, you will get RR. Okay, so this is important, this is important question. Wood's fatigue also discussed, fatigue also we have discussed all these reactions. So I'm just moving forward, will not take more time. Now let's move to question number 36. Why Grignard reaction should be carried out under dry condition? This is important question. Now see, what is Grignard reagent? RMgX. Okay, here Mg is plus, R is minus. Now if this in the environment, if there is any source of proton, okay, H plus, this immediately R takes this proton and we get RH, which is your hydrocarbon. We will not be getting the desired product, immediately we will get the hydrocarbon. So that is why to prevent this we need to have, I can say, dry condition. Okay, so you can see Grignard reagents are highly reactive and react with any source of proton to give you hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to corresponding hydrocarbons. So this is the reaction that takes place. So we need a dry condition. Next, explain with the help of chemical reaction so that the presence of electron withdrawing group fastens the nucleophilic reactions of haloarenes. Now, if you see here, the what happens is, see, if you have a benzene ring, okay, now benzene is a planar molecule. You can imagine the ring to be like this, okay, the pi bond. This is the electron density and this is the electron density. So this benzene ring are itself nucleophilic in nature. Now when you add a nucleophile to this one, there is repulsion. Okay, so if somehow we can reduce the electron density in the benzene ring, then the attack of nucleophile becomes easier. Okay, so that we need to show with the reaction. So you can see here, this is a reaction that is given in the book. If you take simple chlorobenzene, you need 623 Kelvin and 318. If you take one nitro group, the reaction can be done at 443 Kelvin. If you take two NO2 groups at 368 Kelvin, and if you have 3 NO2 groups, it can be done just with warm water. So this shows that with adding of electron withdrawing groups, you can increase the nucleophilic reactions of haloarenes. Next, write the IUPAC name of the major product formed when chlorobenzene is treated with acetyl chloride in the presence of anhydrous AlCl3 and name this reaction. So when you, this is your Friedel-Crafts acylation and you will get this particular product, that is COCH3, right? So how do we name this? And we have already chlorobenzene, right? So here, yes, chlorobenzene. So here you have to name it like this is 1, 2, 3, 4. So 1 chloro, okay, and in this particular, this is carbon number 1, this is carbon number 2. So 1 oxoethyl, okay, sorry, 1 second, yeah, this is, okay, 1 oxoethyl benzene, or you can simply write 4 chloroacetophenone group. Okay, next, what is the name of this reaction? Friedel-Crafts acylation reaction. Next question number 39. Para-dichlorobenzene has higher melting point than ortho and meta. Already we have discussed because of its symmetrical structure. It is fitting better to the crystal lattice, so it has more ortho, like more boiling point. Okay, next draw the structure of DDT and mention one of its uses. So this is the structure of DDT, and what is its use? It was used for, or it was used as insecticide in the past. Okay, next name the reaction involved in the preparation of Freon-12 from tetrachloromethane and mention one of its uses. So the reaction name is Swartz reaction, and it can be used for various purposes. You have to write any one: aerosol, refrigeration, air conditioning purposes. These are the different uses. Mention one use of chlorophene in each field of medical and industry. So in the industrial field, it is used for the production of refrigerant R22, and in medical field, it was used as an anesthetic. Next, what is racemic mixture? Represent butane 2-OL in the racemic form. What is racemic mixture? I have already discussed 2 times. How do we represent it? Because both the enantiomers are present, you have to write plus minus butane 2-OL. Okay, plus minus. Next, write the IUPAC name of the product formed when ethyl bromide reacts with sodium iodide in dry acetone. So this is your Finkelstein reaction. So you will get iodoethane, okay, and the name of the reaction is Finkelstein reaction. Okay, so now we will move to, these are your 3-marker questions, okay? 3-mark question. Now, as I told you, you be not be thinking like that from this chapter we will not be getting 3-marker questions. So why to do that? It is not like this, because the 5-marker can be a sum of 3 plus 2. So you need to do 3-marker questions as well. So let's solve the first question, very interesting one. Okay, so you have a compound M with molecular formula C3H6. Okay, C3H6, and on reaction with HBr forms compound N. So when you react it with HBr, it forms compound N. Okay, now compound N on heating with sodium metal in dry ether. Okay, sodium and dry ether produces X hydrocarbon. Write the IUPAC name of M, N, and X. Okay, now see C3H6, you can see it is a formula of an alkene. Okay, so you will have a structure like this. Okay, so this is what propene. Okay, now when you adding HBr, what will happen? Markovnikov's rule will be followed, and you will have CH3, CHBr, CH3. Okay, now what is this one? This is 2-bromopropane. Okay, now what we have? Sodium dry ether, right? Sodium and dry ether. This is what Wood's reaction. So you will just need to double the product. So you will get a structure like this. I'll just replicate this one. Okay, so if I have 1, 2, 3, 4, okay, so I will get 2,3 dimethyl butane. Okay, that will be the product, that is my X. Clear? So next question, complete the following reaction. Okay, now here I am doing bromination. So what is Y here? Y will be simply addition of bromine. Okay, next we are taking it with Y. Okay, now that will be like Grignard reagent. We are converting it to Grignard reagent, which is I'm getting MgBr. Okay, this is Z. Okay, now if you treat it with RNH2, now amines and then alcohols and water are great source of hydrogen. Okay, so immediately we have understood that once this acidic hydrogen is there, you will get back your H. Okay, that is your benzene. The final product will be benzene in this reaction. Next, name the alkyl chlorides are reacting with sodium iodide in dry acetone to give you alkyl halide. So name of this reaction, all of you know, this is Finkelstein reaction, right? What is the general equation? You have Rx plus NaI in dry acetone, right? You will get Ri plus NaX. Next, mention the role of acetone here. So that I have given here. So the NaCl or NaBr that is formed in the reaction, okay, that is precipitated in the dry acetone. In dry acetone, it gets precipitated. It facilitates the forward reaction according to Lee-Chatterley principle. So if this dry acetone will not be there, then there may be a reverse reaction. So that is why you need to separate this NaX and NaX, that is which is formed, that is using dry acetone. Okay, next we'll do question number 4. Write the steps involved in the conversion of 2-chloro-2-methyl-butane to 2-methyl-butane 2-OL, and what type of solvent favors such reaction. So first of all, this is SN1 reaction. Okay, you can see tertiary compound is there, and already we have discussed this one. What type of solvent? Polar protic solvent will favor. Okay. Next, write the steps involved in the ethyl chloride to ethanol. This is SN2 mechanism. This also we have discussed. What order of kinetics it follows? It follows second order kinetics. Next, why haloarenes are less reactive towards nucleophilic substitution? Mention 3 reasons. This also we have discussed in the starting of the question. Here, sixth one, important question. The first reason is the resonance, right? The second reason is your sp2 hybridized carbon. Okay, and the third reason is your instability of phenyl carbocation. Okay. Next, with the help of resonance structures show that the presence of nitro group on the meta position does not affect the reactivity of haloarenes towards nucleophilic substitution reaction. So in the previous question we have discussed that if I add nitro groups, okay, it will withdraw the electrons from the ring and make the ring more electrophilic, and now the nucleophile can attack in a better way. But if you have seen, we have also shown the examples, the nitro group should be attached at only ortho and para position. The question is saying that you have to draw the resonating structures and show that if the nitro group is present at the meta position, it is not able to withdraw electrons from the ring. So that is there already in the book. So you can see if there is a nitro group at the meta position. So if this OH is attacking, negative charge will come on this carbon, then again this one will go, and then the negative charge will come on this carbon. You can see that the negative charge is not going to the NO2 ring at all. Okay, then again it will come here, then here, it will be moving in this ring only. Okay, it will not go to the NO2 part. So that is why in the meta position it cannot withdraw electrons. Next, with the help of resonating structures, explain why chlorine directs the electrophile towards ortho and para position in spite of being an electron withdrawing nature. So this we have already explained once, because chlorine has lone pairs of electron, it can donate to the ortho and para position, but you have to show using the resonating structure. This question is there in your in-text question, so that is why this becomes important. So you can see that when the ring attacks the electrophile, there is a positive charge formed here, and this positive charge is highly unstabilized because chlorine has minus I effect. Okay, then chlorine, what does it do? It donates the electron and makes the ring a bit stable. Okay, so that is what you have to draw and show here. Next, we'll go to question number 10. Primary alkyl halide C4H9Br. Okay, so there is A, which is C4H9Br, reacted with alcoholic KOH to give you B. Alcoholic KOH to give you B. Now compound B reacted with HBr, okay, to give you C, which is an isomer of A. C, what is the relation? It is a isomer of A. Next, write the structure A, B and C. Okay, so if you see C4H9, it is a primary alkyl halide. So the only structure that is possible is, I have something like this. Okay, now with alcoholic KOH, what will happen? There will be a double bond form here. Okay, now with HBr, what will happen? There is addition of HBr, Markovnikov's rule will be followed. So we will have CH3, CH2, CHBr, CH3. Okay, so you can see these two are positional isomers, A and C. Next, racemic mixture, enantiomers, optical isomers, we have discussed all of them. Now let's move to question number 12. Write the equations for the steps involved in the mechanism for the conversion of tert butyl bromide to tert butyl alcohol among polar protic solvent and non-polar solvent, which solvent is generally used. Already discussed, polar protic will be used. Next, out of C6H5CH2Cl and C6H5CHCl C6H5, which is more easily hydrolyzed by aqueous KOH, and justify your answer. Now see, this is an important question. This hydrolysis, no, it follows SN1 mechanism. And if it follows SN1 mechanism, what will drive the reaction? The stability of carbocation. Okay, now you see in the first one, if you have C6H5CH2Cl, carbocation formed here is CH2 plus. And in this one, you have C6H5CH, C6H5, and you have a carbocation here. Now you can see that this particular carbocation is stabilized by resonance, but this carbocation will be stabilized by 2 resonance. So obviously this is more stable. Okay, this is more stable because here we have more resonance, right? So that is why what I can say, which one will be more easily hydrolyzed? The second one. Okay, next, you can see the detailed answer here. I'll just erase one. Okay, so you can see the same thing here. This is the carbocation formed, here this is the carbocation formed. Out of 1 and 2, the carbocation 2 is more stable because 2 phenyl rings are attached, or 2 carry the positively charged. Okay, next, complete the reaction. This is very simple one. You have to follow Markovnikov's rule. So I have here CH2, here H will attach, and here Br will attach, right? So this will become CH3, CHBr, and CH3. Okay, next, sodium dry ether. So now see, it is, you have to break the molecule in exactly symmetrical manner. So if you take this one, okay, 1 2 3, no, sorry, I need 2 carbons only. 1 second. Okay, so if you have 2 carbons and you just react with sodium ether, Wood's reaction, you will get this product. Next, NaOH 623 at 320 300 Kelvin. This is the addition of OH, nucleophilic addition under high temperature and pressure. Okay, fine. Next question, write the chemical reaction for the conversion of 1 bromopropane to 2 bromopropane, and then name the rules and principles involved in the above conversion. Okay, 1 bromopropane to 2 bromopropane. So you can see here you have 1 bromopropane. So first you have to use alcoholic KOH. Okay, that will give you what? That will give you dehydrohalogenation, and you will get the product here. Next, you have to treat it with HBr, and you will get 2 bromopropane. Name the rule or principle. So what is the principle used here? Markovnikov rule. Okay. Next, the treatment of alkyl chlorides with aqueous KOH leads to the formation of alcohols, but in the presence of alcoholic KOH, alkenes are the major product. Explain. Yes, this is a good question. Now, if you have the same thing, if you treat it with alcoholic KOH, you get a double bond, but if you treat it with aqueous KOH, this Br will be replaced with OH group, right? So what is the difference here that we have to understand? See, this is answer number 16. So the size of the nucleophile is different. When you take aqueous medium, aqueous KOH, the nucleophile there is OH minus, which is very small. Okay, and if you take alcoholic KOH, there the nucleophile is actually C2H5 minus. So what happens, which is bulky? Now this bulky nucleophile cannot go and replace a halogen. It's a bulky one. So what it will do? It will try to abstract the nearest acidic proton. And if it abstracts the proton, what we get? We get an alkene. Okay. So the bulky nucleophile finds it easier to abstract a proton rather than to attack a tetravalent carbon to form a substituted product. Okay, so it's better to abstract a proton and form a double bond. The C2H5O minus attack a carbon carrying halogen. Steric repulsions can delay the attack and prevent substitution. So the basic thing is, in the case of alcoholic KOH, we get a bigger nucleophile which is more supports the ejection of a proton, so that we can have a eliminated product. Okay, next, SN2 mechanism. One second. SN2 mechanism already discussed. SN1 mechanism already discussed. Next, see question number 19. So first we will get red phosphorus, so you will get CH3Cl. Then you have Na and dry acetone, that is CH3I, Finkelstein reaction. Okay, then if you treat it with one second, B, C6H6I and sodium and dry ether. So again, this is what your Woods fatigue reaction, and you will get a compound like this. Okay, this is your C. Okay, now we'll go for 5-marker question. Okay, so the first question here is primary alkyl halide C4H9Br. So what is a C4H9Br? It is a primary alkyl halide. Reacts with alcoholic KOH to give you B. Okay, it reacts with alcoholic KOH to give you B. Now compound B is reacted with HBr to give you C. Okay, which is an isomer of A. So C is an isomer of A. Okay. Now when A is treated with sodium metal, it gives compound D. Okay. Next, C8H18. Okay. Which is different from the compound formed when N-butyl bromide is reacted with sodium. Okay. Give the structure formula of A and write the reactions equations for all the reactions. Now see, C4H9 is a primary one. Okay, so what are the possible primary alkanes, haloalkanes I can form? One is this one. Okay, another structure I can form is this one. Right, now the third, like I can say the last clue that is given, that D which is formed here is not the one which this product will give. That means A is not this one, rather A is this one. So what is the structure of A? CH3, C, CH3, H, CH2, Br. Okay, this is the structure of A. Clear? Next, when you treat it with alcoholic KOH, what will happen? You will get a double bond. Okay, so you will have CH3, CH, double CH3, and here there will be elimination. One second. Okay, next if you treat it with HBr, okay, here Br will be attached, so I'll have CH3, C, CH3, and here Br is attached. Okay, so that is A, this is A, this is B, and this is C. Now when this one is reacted with sodium metal, okay, that is your Woods reaction. So I'll just clear this area. One second, so that I can write the product here. So what will this give me? This is Woods reaction. So you will have like this a structure. Okay, and again the same structure will be repeated here, right? So I'll get 1, 2, 3, 4, 5, 6. So I can say 2, 3, 4, 5, and 6. So 2,5 dimethyl hexane. Okay, clear? Next, let's move to question number 2. A compound M is there, okay, with molecular formula C3H6. It reacts with HBr to give you N. Reacts with HBr to give you N, which on reaction with sodium metal in dry ether produces P. Sodium metal dry ether produces P. Now compound N on reaction with the reagent R yields you M. Okay, so one second. Compound N with the reagent R gives you M, and compound M on reaction with X produces compound N. Okay, write the structure of M and P and reagent R and X. Okay, so first of all it is C3H6, so we know that this has to be a propene structure. Okay, now when you treat it with HBr, what I will get? You will have Marconic of addition, you will get this particular compound. Next, HBr to give compound N, so this is N and this is M. Okay, which on reaction with sodium metal, okay, which on reaction with sodium metal dry ether gives you P. So the structure of P is this one. Okay, this is P. Now compound N on reaction with reagent R gives you compound M. So compound, what will be this one? Alcoholic KOH, dehydrohallucination, right? HBr will be removed and you will get this one. Now compound M on reaction with X produces isomer of compound N. Okay, so if you treat this M with HBr and peroxide, right, so what I will get? I'll get 1 bromopropane, right, which is an isomer of N. So write the structure of M, N, P, R and X. So what is M here? M is your propene, CH3 CH double bond CH2. Now what is N here? N is 1, sorry, I can write 2 bromopropane. Okay. Next, what is P? P is, I can write like this, CH3 CH CH CH3. Here we have CH3 and here we have CH3. Okay. Next we have R, and R is equal to, what is R here? Alcoholic OH. Okay. And then X. X is the, X is your HBr peroxide. Okay, clear? Next, let's move to third question. A researcher performed a reaction on 1-butene, okay, 1-butene, okay, with HCl to yield a compound A, which rotated the plane polarized light. That means it is optically active. Okay. Next, so I can also predict the structure of A, so it has to be this one, right? Now he then treated compound A with KOH, aqueous KOH, to produce compound B. So in aqueous KOH, what will happen? The Cl is converted to OH, so that is your compound B. When compound A was heated with reagent C, okay, he got compound D. That was isomer of 1-butene. So if you take this one as alcoholic KOH, okay, so what you will get here? You will get a structure like this, but2-ene, which is an isomer of A, that is but1-ene, right? Which was an isomer of 1-but-ene, right? So this is A, but2-ene. This is not A. This is but1-ene, and this is but2-ene, right? So they are isomers of each other. Next, write the structure of compound A, B, and D. So this is A, this is B, and this is D. Okay, and mention the reagent C, that is alcoholic OH. What will be the optical activity of compound B? So compound B is also optically active. Why? Because it has a chiral carbon. Okay, fine. Now let's move to the last question of this session. In the laboratory, a student named Sanju, okay, 1 second. A student named Sanju of 2nd PU reacted organic compound X C3H6 with HBr. C3H6, we know it is propene, okay, and it reacted with HBr, so you will get 2 bromopropane, right, to get a compound Y. And later he repeated the same reaction along with hydrogen peroxide to give compound Z. So if you have HBr with peroxide, so what will happen? Br will be attached here. So here we have like this. Okay, that will give you compound Z. Next, he made to react compound Y with sodium metal. Okay, now that will in ether to get you compound A. So what will happen here? Again, Wood's reaction, right? So that is there. This is A. And similarly, Sanju reacted compound Z with sodium metal and ether to give you compound B, right? So that will also be a compound like this, that is B. So identify compound X, Y, Z, A and B. So what is X here? X is propene, right? CH3, CH double bond, CH2, that is propene. Next, what is Y? Y is CH3, CHBr, CH3, that is 2 bromopropane. Okay. Next, what is Z? Z is 1 bromopropane. Okay, because it is Markovnikov addition. And A is what? A is 2,3-dimethyl butane. Okay. And what is B? B is hexane. Okay. So we have got X, Y, Z, A and B. So I'll just make, yeah. So this is my X. This is Y. Okay, 1 second. Okay, fine. So we have got X, Y, Z, A and B. So with this, we have discussed all the important questions from this particular chapter. Now I want to give you the list of most important topics that you must not miss. Okay. The first thing is whatever questions I have rounded or written VVI, definitely do them. And the most important thing here is SN1 and SN2 mechanism, then all the name reactions, okay, and then some definitions like racemic mixture, enantiomers, okay, chirality. These are some important definitions. Then there are some reasoning questions, okay, which is very, very important. The first one is haloarenes are less reactive. Haloarenes are less reactive towards nucleophilic substitution reaction. The 3 point is there: resonance, hybridization of sp2, and stability of phenyl carbocation. Okay, so these are the most important topics that you must revise. So children, here the chapter ends. We have solved all the important questions. If you need this PDF, please join my WhatsApp channel. The link is there in the description section. And also, if you want a PDF of only important questions, like 15 to 20 important questions from this chapter, do comment me. I'll be providing you that also in my WhatsApp channel. So thank you so much for watching, and after doing these many questions, you will be super confident on this chapter, and 9 out of 9 is guaranteed here. Okay, so thank you and all the best.